Hey guys, this is Mrs. York, and today we're going to talk about the life cycle of a star. Feel free to pause or rewind as we go through the slides so that you may take the necessary notes. Out there in space, there are huge clouds of dust and gas known as nebulas or star nurseries. They're called star nurseries because this is where stars are born. These clouds are made up of hydrogen and helium. If a cloud is massive enough, its own gravity will cause it to collapse and fold in on itself towards its center. As the cloud begins to get denser and hotter, the hydrogen and helium atoms start to stick together through a process called fusion. This process is the energy source of a star. So here's a picture of a stellar nebula. As gravity causes the gases to fuse, it begins to heat up and spin fast. A star is finally born, also known as a protostar. Once the star switches on and becomes alive, it spends most of its life fusing hydrogen atoms to make helium atoms. At this point, the temperature eventually reaches 15 million degrees Celsius, and nuclear fusion occurs in the cloud's core, causing it to grow brightly. Inside the newborn star, hydrogen atoms are fused together to make helium atoms. So a protostar is the stage of a star's life cycle in which it is actually split from the nebula, but it hasn't approached the beginning of nuclear fusion. It is surrounded by a thick layer of gas and dust, so it blocks visible light. However, scientists are able to view protostars through special telescopes that pick up the different waves. They can also see protostars by viewing the jets that are expelled out of the center of the star. Here are a few pictures of what a protostar looks like. In the middle, you have the protostar, and it is exploding gas and dust through its center on both sides. And then you have the accretion disk. And the accretion disk is what's left over from the nebula. So once this star begins to contract a little, it still remains stable. Once it's stable, it's known as a main sequence star. Hydrogen fusion supplies the main sequence star with the support to prevent it from collapsing. A star normally spends 90% of its life in the main sequence stage. However, different stars age at different rates. The hotter the star is, the shorter its lifespan will be. So here's a picture of a main sequence star. What happens to a star during the rest of its life depends on how massive it is at its birth. A star like the Sun is in a delicate balance with gravity. So of the billions of stars that exist in our galaxy, the Sun is the closest star to our Earth. The Sun is 1.5 million kilometers in diameter. It is not the largest star in our galaxy, although it may appear to be so because of its distance to the Earth. It is a medium-mass star in its main sequence stage of life. It's currently over 4.5 billion years old and halfway through its life. The Sun is composed mainly of hydrogen at 75%, 23% is helium, and the other 2% are made up of heavier elements. The Sun's core is 27 billion degrees Fahrenheit, and its surface is 10,000 degrees Fahrenheit. So like I said, size matters. There are three different stars. There is the low mass star, the medium mass star, and the massive mass star. These three stars are different based on their mass and the path of their death. Although these stars may vary in size, they share the same thing in common. They will eventually run out of fuel and collapse. At some point in a main sequence star, the hydrogen runs out. At that point, the core of the star will collapse in on itself under its own weight. It gets denser, it gets hotter, until the point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing the helium atoms together, making carbon and oxygen, the next heavier elements on the periodic table. As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our Sun will grow so large it will swallow up the inner planets of our solar system out as far as the Earth. It will become a red giant. For the Sun, this will be the beginning of the end. What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. Actually, the star loses hold of its outer atmosphere. Its outer atmosphere starts to drift off out into space. It expands to become a planetary nebula. Here are a few pictures of the stages of the red giant, and from there it turns into a supermassive red giant at 4,500 Kelvin. So once the outer layers have drifted away, all that is left of the star is its core. So planetary nebulas are created by medium mass stars. They occur during its collapse from a red giant to a white dwarf. The outer layer of the star is exploded and creates a cloud of gas. And here you can see the planetary nebulas. Once the outer layers have drifted away, all that is left of the star is its core. A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. It's something that might weigh as much as half the mass of the Sun, but it's only the size of the Earth. So it's an incredibly dense object. It is dead, so there's no nuclear fusion going on anymore, but it's incredibly hot. After hundreds of millions of years, it will eventually cool down. And here's the picture of a white dwarf. So once it cools down, it's going to turn into a black dwarf star. Black dwarf stars take hundreds of billions of years, so our universe is only 13.7 billion years, so they don't exist yet. But this is what we think a black dwarf star would look like. Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core, all the way from hydrogen to magnesium. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun until it has fused elements all the way up to iron. Once we've formed an iron core, there's no more energy that can be made from fusion. The core collapses, the rest of the star starts to collapse in after it, but then it bounces off. There's a huge shockwave explosion. This is a supernova. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy. Here are a few pictures of some supernova. For these supergiant stars, all that is left is super dense core. This core is known as a neutron star. An object that can have a mass greater than our Sun but less than 20 kilometers across is a neutron star. But for the most massive stars of all, we think that when the core collapses, the gravity is so strong it becomes a black hole. The gravity is so strong in a black hole that not even light can escape it. However, scientists have found evidence of the existence of black holes by seeing objects that are quickly pulled into an open area. Any object that moves too close to a black hole will be pulled in by its gravity, and you will never see it again. It basically pulls the atoms apart. Here's a picture of what a black hole would look like. After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars. The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the Sun and planets were formed. And when that star died and blasted out into space, that formed the raw materials from which our Sun, the planet Earth, and ourselves were made. And ultimately, that's one of the major reasons I think understanding stars is critical, because it's actually telling us where we came from. In this slide, it's just a diagram of the different stages. So when you come to class tomorrow, we're going to fill out a graphic organizer of the different steps that a star will go through, depending on its size. So if you need to, go back, take some notes, and come back to class tomorrow, and we will go over the life cycle of a star. Thanks for watching.